Here I am trying to explain in a very simplified manner what actually the non-degenerate or degenerate gases are, or what is the concept degeneracy. This I am trying to explain with the help of this diagram. In the first one I have tried to show a classical ideal gas. Second one, or the one in the middle, is showing boson gas, and the last one is showing a fermion gas. The gas behaves as a classical ideal gas when the temperature of the system is high, the density of the gas is very low, and the particles or of the gas, they do not have any force interactions. This situation is purely governed by the laws of classical mechanics, but on the right hand side in two diagrams, the fermionic and bosonic gases are shown. Such systems correspond to very low temperatures, high density of the gas, and there are no force interactions among the particles of the gas, but the quantum mechanical effect of identical particles exists. Degeneracy is basically the deviation in behavior of a gas from that of a classical ideal gas. Degeneracy sets in when temperature of a gas is lowered. Complete degeneracy corresponds to absolute zero of temperature. Now, as the diagram shows, the classical mechanics governs a system in the regime when the distance between the particles of the system, say we represent that distance by r, that is much larger than lambda, where lambda is the wavelength of matter waves associated with the particles of the system. But quantum mechanics comes into picture and it governs the system in the regime when r approaches lambda. That means the distance between the bosons or the fermions or the particles of the gas that approaches a value which corresponds to the wavelength of matter waves associated with them, then there arises a possibility of overlapping of these waves. Here also there are no force interactions among the particles, rather due to this possibility of overlapping of the waves, the quantum mechanical interactions among them, they play a role, and we observe this degeneracy. In case of boson gas, the bosons do not obey Pauli's exclusion principle. So as shown in the diagram here, the different bosons can occupy the same energy level, but in case of fermions, the particles of the gas are obeying Pauli's exclusion principle. So when the temperature of the system is lowered, the particles try to acquire the lower energy states, but due to Pauli's exclusion principle, they acquire separate energy levels, and the highest energy level which is occupied by the system at 0 Kelvin is called Fermi energy level. So it is clear from the diagram shown here how the three types of gases behave. The first one is explained by classical statistical mechanics, and the other two diagrams are explained on the basis of quantum statistical mechanics. And the main difference is the Pauli's exclusion principle. It is not obeyed by the bosons, so they are showing condensation in the lowest energy level, while due to Pauli's exclusion principle, the fermions are filling the states one by one, as shown in the diagram.